Show the 6th-degree Taylor polynomial for f about x equals 5 approximates f of 6 with error less than 1 over 1,000. So this is an error question. An error question means I'm going to do one of two things. Either it's an alternating series, and I'm going to be able to figure out the error based on looking at the first term I leave off, right? If I do an alternating series and I use the first 7 terms, my error is going to be no bigger than the absolute value of the 8th term. Or it's going to be a Taylor's theorem application where I find the Lagrange error, and that's just, if it's not alternating series, it's going to be a Lagrange error question. So I think this is a Lagrange error question, unless it's alternating. Oh goodness, there's some phrase I want to say here to express my joy, but no phrase captures it fully. Alternating is so much easier than Lagrange. Not that Lagrange is hard, it's just a pain. So, those emails come in. So, I have an alternating series. 6th-degree Taylor polynomial. I know what my 6th-degree Taylor polynomial looks like. My 6th-degree Taylor polynomial looks like the 3rd-degree Taylor polynomial. So it looks like this whole thing. Copy, and paste, and I don't need you anymore, and I can take all this, put it closer over here. I really don't need to know that that's called P3 of X. Just, skip ahead for a minute until you get to the part of this video where Mr. Novick is somewhat competent. Oh god, I left off the 1/2. It's just falling apart in front of me. Okay. My 6th-degree Taylor polynomial looks like this. Plus it has some term to the 4th power, plus ... plus it has a term to the 6th power. It ends with 6th degree. The term that has the 6th degree is going to come from this thing up here that's magically now in a box. I'm going to do the 6th degree term using my general formula. It's going to look like -1. If I plug in 6 for n, I'll get it. So to the 6th power, x minus 5 to the 6th over 2 to the 6th, 6 plus 2. That's going to be my 6th degree polynomial with things filling in the ... But I put ... because it doesn't really matter. Even the 6th degree term doesn't really matter. But what this question is saying is that I use this polynomial to approximate f of 6. I say f of 6 is approximately what I get if I plug in 6 into this polynomial. That also happens to be of degree 6. So it's going to be 1/2 plus something plus something plus something, all the way down to plugging a 6 into this term, not E6, plugging 6 into this term. And that's going to give me some approximation of f of 6. A good approximation. 6th degree should be pretty good. How good, though, is measured by what the error is. It's measured by how far I am from the actual answer. I don't know for sure how far I am from the actual answer. If I knew that, I wouldn't be doing an approximation. I just know the actual answer. But I know the error, the amount away I am from the actual answer, can't be more than the first term that I leave off. The first term I leave off looks like -1 to the 7th, because I stopped when n was 6, so now I'll see what it is when it's 7. X minus 5 to the 7 over 2 to the 7, 7 plus 2. So when I plug in a 6 into the polynomial, I'm going to sum up this alternate series, where it's going to be 1/2 minus a 6 times 6 minus 5, plus something, minus something. It's going to be alternating. And the first thing I'm going to leave off is this term that looks like -1 to the 7, 6 minus 5 to the 7, over 2 to the 7 times 7 plus 2. That's equal to -1 times, and the -1 doesn't really matter because my maximum bound on my error, this first term I leave off, I really care. It's the absolute value is what I'm looking at. So -1 to the 7th is -1 times 1 to the 7th over 2 to the 7th times 9. And when I do absolute value of that, that's going to come out to the 7th, 1 over 1152. So what I figured out is this first term I leave off, 1 over 1152. My error is not more than that. My error is less than 1 over 1152, which means it's definitely less than 1 over 1000, because 1 over 1152 is already smaller than 1 over 1000. So my error is definitely less than 1000. And again, the key here was that it's an alternate series. I didn't need to go through the work of Taylor's theorem of finding Lagrange error because it was an alternate series, so I just looked at the first neglected term.